rate or the concentration of electrophile, it shall affect the reaction rate definitely. So this is a second order kinetics. This Arrhenium ion mechanism is second order, but you have seen that this SE1 mechanism is in fact this is the first order. That's why we call it SE1 mechanism. Now, there are a few examples being given here just to elaborate you. Look at the very first example here. This X is chlorine, bromine or iodine and butyl lithium. I already presented. You have seen the organometallics addition. Just like Grignard reagent you are already familiar with, in which we have a carbon bonded with a magnesium metal. Here it is bonded with lithium metal. So this is also organometallic. So when it is resulting, it is a very strong base. The negative charge on butyl picks up this halogen from here without electron pair. So it takes this electron pair here, generating a negative charge on this carbon. As a result, this counter ion lithium make a covalent bond with this carbon. So we are having a lithium carbon bond. This is equivalent that this carbon bonded with the metal, this carbon is negatively charged, right? This is equivalent of that. In next case, we are reacting this with a electrophile. This Y is an electron. In fact, this is something which is going on to bond. Basically, this R and Y, R doesn't mean here alkyl group. Keeping in mind, if it is alkyl group, this is electron deficient, Y is more electronegative. I have just presented that this Y is electron deficient. So this negative charge approach this Y, generate a bond here. This R doesn't mean, keeping in mind, this is not an alkyl group. So let's see, there are various other methods with the help of which we can generate a carbanion. Let's say this is a benzaldehyde. When benzaldehyde is reacted with a base, sodium hydroxide, if you remember, this is Cannizaro's reaction. In Cannizaro's reaction, when this hydroxyl group adds to this, it results in this. What happens in that case, this oxygen donates this electron pair off, and this electron pair takes off this one. So what comes out here, we already have a hydrogen present on this carbon. Oxygen makes a double bond and then OH. So what is this? This is a formic acid, or formic acid eliminate and results in the formation of a carbanion. So this is how we can generate an carbanion again. We shall again react with an electron deficient Y, which is an electrophile, to result a carbon Y electrophile bond, right? So look at another method. If we react this aldehyde with Grignard reagent, rather we are reacting with n-butyl lithium. So if we add this, so this magnesium phenyl shall be inserted at this place. This is in fact, keeping in mind, this is not aldehyde, just make a correction, this is an ester. So this has been just copied from here. So I have missed here. It is an ester in fact. So just this is a methyl benzoate. So just write here oxygen bonded with alkyl group, maybe methyl. So first phenyl addition takes place and then it generates a ketone. Ketone again undergo. So we have two phenyl groups present, generates a tertiary alcohol. This is what you have already come across. Whenever Grignard reagent with that reacts with an ester, it always forms a tertiary alcohol. You see, this is a tertiary alcohol. Alcohol oxygen attached to a carbon which is bonded with three atoms, carbon atoms. So anyhow, this oxygen donates electron pair off here, and this donates this electron pair off, resulting the elimination of this group, which is called benzophenone. So benzophenone is eliminating and resulting in what? A carbanion. So a carbanion can be generated starting from an ester reacting with Grignard, or reacting in any aromatic aldehyde with an base. Shouldn't have an alpha hydrogen present. Then in all of these methods, or if we are using n-butyl lithium, so this is also useful. So we are getting a lithium carbon bond in fact, or carbon-9 is generated, carbon-9 is generated. So this is how we can generate. So if we generate carbon-9 first and then we react this with electrophile, so it shall always be a unimolecular order reaction. So it shall not depend upon the concentration of nucleophile. If we are increasing or decreasing the concentration of electrophile, it shall not affect the reaction rate. This is the reason the chemical kinetic data, again you can see, is helpful here to devise the reaction mechanism. So when we were doing this electrophilic substitution reaction involving these protocols, and when we increase the concentration of electrophile, it didn't affect the reaction rate. This is the reason why we are being switched over to this mechanism. So anyhow, this is all over the SE1 mechanism that you have already come across today. So this is an second mechanism, which is a uni order reaction, and the previous one, arenium-ion, is a second order kinetics. That is a total difference between both of them. Arenium-ion mechanism also depend upon the concentration of electrophile, but SE1 mechanism doesn't depend upon that. So if we are doing a reaction and the reaction is dependent upon the concentration of electrophile, it reaction rate is affected, then it is definitely following arenium-ion mechanism. If it is opposite, the change in the concentration of an electrophile doesn't change the reaction rate. It means it is not dependent upon the concentration of the electrophile. So it is a unimolecular kinetics, mean following a SE1 mechanism. Now let's see proceed further. The third kind of mechanism that we commonly refer as simultaneous attack and departure mechanism. This is a very interesting mechanism which is very, very rarely observed. What it means? It means it is a concerted mechanism. If you have seen before, both two mechanisms, arenium-ion mechanism and SE1 mechanism, they are stepwise. Arenium-ion mechanism, first step is slow rated, second is fast. Same is for uh, SE1 mechanism. Both have first step slow, second fast. But in one case, arenium-ion mechanism, after first step, a carbocation is generated. And electrophile is involved in first step. In second SE1 mechanism, you have seen after first reaction, slow rated step, a carbon-9 is generated, rather a carbocation. Second difference, the electrophile is involved in second step, which is fast rated. These are the two major differences between arenium-ion and SE1 mechanism. Both are stepwise. This is a common feature among both. But third mechanism is simultaneous attack and departure mechanism. In this case, mean the a group which is to be substituted by an electrophile is leaving and electrophile is approaching at the same time. This is called simultaneous attack and departure. Means this is a concerted mechanism, completes in a single step. I have presented here an example. So two examples. First one is presented as a general concern. Let's say we have an X group present, maybe any group, which is living without electron pair. So it is donating this electron density here. This electron density is transferring here. This pi electronic density is transferring here, and this pi electronic density transfers to the Y. Now here, see, this group is leaving, and new electrophile is approaching at the same time. This is what we call simultaneous attack and departure. Very few reactions you shall find following this mechanism, but there are. In fact, we cannot deny their presence. For example, let's say if we have a trimethyl phenyl group present at this position, and we react this with chlorine, there is no Lewis acid we are using in this case. In our rhenium ion mechanism, you see whenever we react halogen, we use our Lewis with BF3 or aluminum trichloride, etc. Any one of them we are using. So anyhow, when we are using a fluoride ion have a high affinity with silicon, it makes a bond with it. At the same time, when it is making four bonds with it, this electron pair transfers here, this electron pair transfers here, this electron pair transfers there, and this pi electronic density transfer towards this chlorine, and this chlorine takes this electron pair off. So we get a trimethyl silyl fluoride, and a chloride ion eliminates, and this chlorine substitutes this one. So this is a following single step, right? So uh, electrophile is involved here. So what is the order of the reaction in this case? This is a second order as well, but it is not following the formation of an intermediate. This is the only difference between. Uh, it is also second order. The rhenium ion mechanism is also second order, but difference is, if we see the kinetic data shall be same for them, but it is rhenium ion is involving the formation of a intermediate, but this is not involved in the formation of an intermediate. This is involved in the formation of a transition state, in fact, right? This is a difference between rhenium ion and simultaneous attack and departure mechanism. Right, so in the bottom, I have presented a very interesting synthesis, just the application of these mechanisms that you have already come across, just their application. Just see what we are having. This X is hydrogen, and if it is methyl, this is commonly called toluene. We are starting from toluene, which is a petroleum product. Petroleum products. It is isolated from the crude oil. So very not expensive. Just 2.5 liter of that cost a few thousand, 2 to 3,000 only bottle cost this. So we are starting it from here and look at involving these number of steps what we have synthesized. A saccharine. Saccharine is a artificial flavor. This is more sweetened than sugar, but it has certain drawbacks. It affects our throat, and in fact, it causes a infection of that. So it is no good for us to use, but it is more sweetened than sugar. Used long time ago as an alternate of sugar, but and it was used for diabetic patients because they can use this, but it has certain other disadvantages. So it is no longer being used as a artificial sweetener. We are getting used uh, aspartams. Aspartam, all this candrel or any other sweetener, sucrol, so etc. All of them are aspartam, which is a peptide in fact. So sometime else I shall present the structure of aspartame. So saccharine is no longer being used. Now see, long time ago how saccharine, when it was in demand, how it was synthesized. All of this is aromatic substitution reactions. Just see, when this X is hydrogen, this is toluene, right? If we are reacting this with oleum, you see H2S2O7, this is called oleum. So it causes sulfonation. So this is methyl. So it shall orientate this to ortho and para to substitute. So we get here a sulfonation at this place, sulfonation at that place. We take this isomer separated, and then in next step what we are doing, we are converting sulfonic acid. Sulfonation was carried out. X becomes sulfonation upon reaction with, this is what you have seen in rhenium ion mechanism. If we have a sulfonium ion generated, so sulfonium ion generated shall replace this hydrogen generating sulfonic acid. When this sulfonic acid is reacted with SOCl2 thionyl chloride, it converts into sulfonyl chloride, SO2Cl, right? So OH is replaced by Cl only. This is all sulfonyl chloride in fact generated. Then this sulfonyl chloride is reacted with ammonium carbonate. Ammonium carbonate is a source of ammonium ion, but this chloride it adds to convert into sulfonamide, right? This is sulfonic acid, this is sulfonyl chloride, this is sulfonamide. These are the three functional group which is converting using these reagents. Very first, sulfonation. Second is sulfonic acid is converted into sulfonyl chloride, just a functional group derivatization, and sulfonyl chloride is converted into this entity, sulfonamide. When this X is sulfonamide here, it is reacted with aqueous potassium permanganate. You have already come across in alkanes chapter that if an alkyl chain is bonded with an aromatic system, whatsoever is the number of carbon, this is 2 carbon, 3 carbon, 4 carbon, 10 carbon even, then it all oxidizes with potassium permanganate hot concentrated solution. Temperature hot on heating and concentrated solution of aqueous KMnO4 oxidizes side alkyl chain to carboxylic acid. This is what you have seen already in alkanes chapters. So anyhow, once this is being generated, what is the next step? You see this nitrogen act as a nucleophile. One hydrogen from nitrogen and a hydroxyl ion from here leaves to form a nitrogen carbonyl carbon bond, which is this one, nitrogen carbonyl carbon bond. So one water molecule leaves from here and generates one very interesting isomer, which is commonly called saccharine, artificial sweetener. These are the three mechanisms which are involved in aromatic electrophilic substitution reactions. So we shall focus on, in fact, substitution aromatic nucleophilic. So today I shall just finish this off, and then we shall have some other topics remaining that we shall start tomorrow, inshallah. So you have seen electrophilic aromatic substitution, but here it is substitution aromatic but nucleophilic. Mean nucleophile is used. When nucleophile is used, when our aromatic system is electron deficient, it is not electron rich, then nucleophile can approach this. Now let's see some substrate. This is aromatic system. This is aromatic system, but you see it has two nitro groups present here. This is nitro group. I have opened one nitro group here. This nitro is also like this, but I have just opened one nitro. What is the influence of the due to resonance? If we take this electron pair off, this electron pair shall be transferred here as a resonance, so we shall get a positive charge here. Similarly, this electron shall transfer is generating a positive charge here. This shall transfer there in other resonance form, we shall get a positive charge. So this nitro group is creating at ortho position and para position positive charge. Now look at the effect of this nitro, very similar to this. So it is generating at ortho position and para position positive charge. So this same three carbons are becoming electron deficient full positive charge due to these two nitro groups. As a result, you look focus here, this carbon which is bonded with X. X may be chlorine, bromine, iodine, sulfonyl, sulfide, silanoxic entity, or some other sulfonyl, phenyl, etc. So it can be a very good living group. If it is a good living group, this carbon is electron deficient. Rather, it donates this electronic density to an electrophile. It is now you see all carbon atom here are electron deficient. How they can donate electronic density to an electrophile? They are not going to do it. But a nucleophile can approach here. So if this X group is any of them, then it shall add here, right? And kicking out this X from here. So it is following very similar mechanism. First, where electrophile was added, generating a carbocation, but here, look at here, this is generating a carbanion. Nucleophile adding here, and then X leaves with electron pair. This donates this electron pair back, and this step is a fast weighted step. Now you can see this is a second order kinetics. It is containing. It is depending upon the concentration of the aromatic system substrate as well as nucleophile. So it is a second order with respect to rhenium ion mechanism, but it is not generating a carbocation or rhenium ion. It is generating a carbanion in fact, and it is not reacting with an electrophile. This is reacting with a nucleophile. These are the two variations. So if we have an electron deficient system, then it can only react. So nitro group, maybe one nitro, one carboxyl group is present, right? So this is happening to electron deficient substrates only. Very rare this we normally observe. Another method that we can make our system electron deficient, for example, let's say this nitrogen is present, amino, this is called aniline. So if this nitrogen, when is present here, this is increasing the electronic density on this aromatic system. So it shall very rapidly reacting with the electrophile. But let's see, when we react this aniline with nitrous acid, you are familiar with how nitrous acid is be generated by the reaction of sodium nitrate, nitrite, NaNO2 with HCl. It generates in situ HNO2, which we call nitrous acid, which is very reactive. If you remember, it reacts with primary amines, generating diazonium. This diazonium is generating this carbon electron deficient, very electron deficient. So what shall happen? It shall generate a positive charge. This shall leave first, or at the same time a nucleophile can approach. Nucleophile can approach, resulting same this one. This is in fact a SN1 mechanism. This is a different mechanism. This is following the second order kinetics, very similar to rhenium ion mechanism. But look at here, this is following the SN1 mechanism. Substitution, nucleophilic, unimolecular. First, uh, carbocation is generated. In next step, nucleophile is reacting. This is stepwise, right? Very similar to here, stepwise. First step is slow, second step is fast, because it is a reaction between two opposite ions, negative and positive. So this is a SN1 mechanism. It is just like we have seen SE1 mechanism. This is very similar to that. It is SN1 mechanism. In SE1, we are having a carbanion generated, but here it is SN1. It is positive charge generated here, right? So similarly, a benzene mechanism can also be followed. Let's say we are having a X group present here, and we are having a hydrogen group present here. If we are reacting with sodiumide, NaNH2, it shall take this hydrogen off because this is slightly acidic, converting into ammonia. So generating a negative charge at this position. That negative charge shall donate electron pair here, and this X shall leave. X is halogen, right? So it shall generate a triple bond, but this is a highly unstable entity. This is a highly unstable entity in highly unstable. So it reacts with another sodiumide. So now this nitrogen can add to this carbon, or this can add to that carbon. It has equal opportunity. That's why we get this nitrogen bonded here, or this bond nitrogen bonded at this position. This is following the benzene mechanism. So you see in this case, this X group is in fact what we are having here. This X is replaced by nitrogen. Truly, this X is replaced by nitrogen. Substitute it, but we are getting another additional product in this case, right? So this is a substitution aromatic nucleophilic, in fact, which is very rare but does happen. So if you have any questions,